everybody. I just wanted to say that the lecture will be conducted in English, but feel free to ask questions in Hebrew and we'll translate. Just wanted to present the community. This is the Big Things community. My name is Levi Ben-Ari, and this is Shlomi Hassan here. We're organizing the community, and we're really happy to see you all here. And I just wanted to present right now Ofer Mendelevitch. He's the Director of Data Science at Hortonworks. He will be talking about the usage of PageRank in anomaly detection in the healthcare data. And I will give him the stage. Thank you, Ofer.
Thanks very much. Very glad to be here. Thanks everybody for coming. I מדבר גם עברית, I speak Hebrew. I grew up here, but I do this talk in English because it's just more convenient. But as Demi said, please feel free to ask me any questions in any language. It's fine. Not any language, but Hebrew and English is fine. So let me get my clicker right here. So as Demi said, I'm from Hortonworks. I've been at Hortonworks for about 2.5 years now. And what I'm going to talk about is PageRank for anomaly detection. Before I do that, Shlomi told me it might be useful for some of you to get a little bit of background on Hortonworks and Hadoop, so I will do it very quickly just for people who don't know what we do and who we are. I literally added this in the last couple of minutes from another slide deck. Before I do that though, yesterday I was listening to the news and there was a big lead-in to my talk today. I don't know if you guys saw, there's a big news item in the US about this gentleman. His name is Dr. Farid Fata. He was a doctor. He had an cancer doctor. And he was convicted yesterday after a long trial in huge fraud in healthcare, which is exactly the topic of my talk today. This is called a horrific fraud because he actually, in order to make money out of illegal fraud in healthcare claims, he actually told patients that they had cancer when they didn't, in order to treat them with drugs and other procedures that they didn't need, in order to send those, they are very expensive, in order to send those claims to Medicare and they get refunded for that. So it's pretty terrible. He's estimated to have made about $17 million out of this. It's terrible, but I just wanted to mention that I edited last night after I saw this news item because it's so relevant. Not all fraud is that terrible and that impactful on patients, but so just very briefly on Hortonworks, we're a Hadoop provider. We're headquartered in Santa Clara, founded in 2011. Actually spun out of Yahoo. Yahoo was the original place where Hadoop was created, and we're now over 600 employees, and you can see some of the other numbers here. What we do is we really invest in open source Hadoop. We're a platform company. We don't sell any proprietary software. We only sell support and services around Hadoop. That's our business model. The one thing that's interesting is that because we spun out of Yahoo, all the main committers and architects of Hadoop actually came with that team. The company was spun there's a team of about probably 30 engineers that were Hadoop team at Yahoo who started the company when it got founded. So that's the quick story around that. And what we do is we really focus on a platform, so we help do things like security and data governance and things that are important for people to use as a really enterprise solution. This is kind of a really quick slide to show like the different components. For those of you who don't know what Hadoop is, it's a big data platform, and one of the reasons I wanted to show this is to show that Hadoop is sort of a piece inside your data architecture. There's a lot of different data sources with different types of data coming in, and there's a lot of applications that people have, and Hadoop doesn't necessarily replace what you have, it kind of fits into what you have. It's another component in your data architecture, and what it's designed to do is to be able to store and process large-scale data. So I'm going to stop here. If you want other things you're going to ask, because I don't want to steal too much time with the presentation. That's my quick intro, just so people know what I'm talking about. So let me go to this talk. This is a talk I did with G1, who of course, is at Stanford and couldn't come today. But I wanted to mention him, and you have a picture, see what he's done. He's a PhD candidate at Stanford. Actually, probably not a candidate anymore. I think he just got his PhD recently. And he's now working at Pinterest. And so we worked on this together. And I'll tell you why in a minute. And so let me tell you about my role at Hortonworks. What I do is I run our data science team. So we as Hortonworks, we don't have data science project internally for ourselves, we don't do. But what we do is we're part of the services organization. So we help customers with different projects that they have. How to use Hadoop for data science, how to do machine learning at scale, things like that. That's what we do. And so, let's see. So what I'm going to talk about is why is fraud detection important in the healthcare community. I'm going to describe the Medicare-B dataset, which is a public dataset of our healthcare data. And I'm going to talk about the work we did of how we approached, how we use similarity functions to build the foundations for doing PageRank. And I'm going to show you a little bit of the implementation, not too much, and then show you some results. By the way, all of this is available on GitHub. This is why I'm not going to go into the code deeply because you can look at it later on if you want. You can also try it for yourself if you want. So that's kind of the outline of the talk. The reason I was interested to do this with G1 is because a lot of the stuff that I see around data science is very generic. It's okay, you do a recommendation engine, use this algorithm, and and it's all the same. And I had this thing in me that I wanted to show a real end-to-end use case. And the problem usually for people like me is that we're not a customer, and the customer data belongs to the customer. So how do you show some really good use case without having access to the data? But when I found this data set that I'll describe to you called the Medicare-B data set, it's a real-world data set that we're fortunate to have. It was released in about 2014 by the Medicare organization. And it's real. And so it was like, oh, wow, this is great. I'm going to use this. I'm going to do something with it. So that led to this work. As you can see. So it's very specific. It's a very specific use case of how you can use Hadoop to do something really cool. All right. So why is fraud a big deal? Well, just because healthcare is so big. That's really the reason. So if you look at healthcare, and this is some numbers I got out of some references mentioned below, you'll see that in the US, the amount of money spent on healthcare is about almost $3 trillion. Sorry. That was important, 3 trillion. This is not 3 billion, this is 3 trillion. So any percentage out of that is a big number. So they estimate that about $171 billion, I sound like Dr. Evil now, but $171 billion in the US alone is going to healthcare fraud. Certain percentages, I think it's between 5 to 10%. And in Europe, it's about 71 billion. So a lot of money. And then recovery rates are about 3 to 4%, so a lot lower than that. So fraud is one of the things where you never know what you don't know and where you're going to recover money from. So these are all estimates, but there's still a lot of money that's not being caught from healthcare fraud. So this is why it's a big problem. And all of the health insurance companies in the US really have a huge incentive to, prevent this as much as they can. Here's a couple other examples, except from the doctor in the beginning. A couple other examples I found earlier. A doctor billing too often for the most expensive office visits. So I just Googled around, you can do that too, and find all these examples of things that are found. I like the second example more. There's a medical supply store, and they sell these motorized scooters for people who have mobility problems. And so there's the expensive one that costs $7,500, and there's the cheap one that costs $1,500. And the doctors, there's a group of doctors, and they kind of did a deal with the store. They prescribe the expensive one, and they provide to the patients a cheap one where they don't understand the difference, and they take the money and split it between themselves and the store. So that was a kind of interesting. There's a lot of really, really intriguing, complicated schemes, but there's so much money to be had, so there's a lot of fraudsters who do all these kind of things. All right. So if you look at fraud patterns, and I had a...
So it's not fraud to be done into medical. It's not pharmaceutical, it is fraud.
Can you repeat the question?
The question was, is this a fraud related to pharmaceutical?
Yeah.
So I'm talking about fraud. Imagine that you're an insurance company and the doctor submits a claim about a procedure you did, like an x-ray or a drug that you may have. I'm not talking about drugs, but you can apply it to drugs that the insurance company pays for, right? And so you want to catch those, right? Sometimes it could be supplies too. All these kind of things fall into that. And here's some examples, right? People bill for services that were not actually performed. This is not what Dr. Fata did. He actually performed bad services that hurt people and killed people. Performing unnecessary services, that's what he did. Using stolen patient IDs, unbundling. There's a lot of coding in the US. They have a really complicated system, but there's a lot of codes that happen. So when you're a doctor, after you treat a patient, you have to submit a claim with a certain, it's called ICD-9 code. It's a code that says this is the procedure that was done. So this is the diagnosis of the patient, and there's a CPT code, which is this is the diagnosis of the procedure that was done. And based on that, you get paid, and sometimes you take a certain procedure that has one code and you unbundle it into 5 different other procedures that seem to do the same thing, but it turns out that you get paid more for that. So there's a lot of these kind of things that are hard to find. So this is the kind of things we want to catch. Now, most healthcare companies that I'm familiar with, that I talk to, they have some kind of system like this. Sometimes a lot of it starts from rules-based systems. So they have a set of rules and they say, well, if this claim for this procedure usually costs this amount of money, and you claim for more than this amount of money, then it's suspect. But they have these kind of if-then-else rules, and quite complicated. A lot of knowledge got integrated into these rules and things like that. Now, some of them have machine learning-based algorithms. So they take the rules-based things and they translate it into a machine learning model, which essentially takes features of the claim, features of the patient, features of the doctor, and build a predictive model for that. And some of the features that are good in this model will be, like I mentioned earlier, claim features. Some of them will be provider features, like you can say, is this doctor submitting a lot of these claims or not? And some of them will be patient features. And these systems work usually a little bit better than a rules-based, depending on the maturity of your model. Now, I'm telling you all this because what I'm going to present to you here is a way to produce a new type of feature. I'm not saying that you want to use this technique to replace the machine learning model altogether. Instead, what I'm saying is, if you got 20 features in your model, if you're a healthcare organization and you want to do that, then I'm going to give you a way to create feature number 21 or 22 or 23 that probably help your model be better. Okay, that's kind of the ultimate goal here. Okay, and we also wanted to use the reason we used PageRank here is one. Well, it's kind of cool, but my co-conspirator in this G1, his PhD was on a system called SociaLite. And SociaLite is a graph algorithm framework. It's a system that allows you to describe a graph algorithm actually pretty concisely. And he translated it into code that runs parallel and computes the graph algorithm quite efficiently. So because I did it with him, it was obvious to use his system. You can ask me later on if it's possible to do in other graph algorithm systems, and it is. But we did it here just because that's the people that were involved in this.
It's open source as well?
It's open source, yes. I'll show, the links will be at the end of the slide, actually. So, and I found also that my incentive was that I see a lot of supervised learning algorithms, predictive models all the time. I don't see a lot of people having success in graph algorithms outside of like Google, Facebook, and some others. So I wanted to find a way to show how graph algorithms could actually be beneficial. A lot of people really like graphs. They're like, oh, it's cool. I can connect the doctor to the patient, I can create relations. But how do you bring it home? How do you make it how do you create value out of it outside of seeing the relationships? Was not really something I saw very, very much. So I had this idea that I wanted to show that. So we're going to show that here. All right. So a lot of introduction. Now let me go into it. So the data set is called the Medicare-B data set. And again, I think we're fortunate I feel fortunate that I have access to this. It's, for those of you who don't know, CMS is a Center for Medicare and Medicaid. It's an organization that provides medical insurance for patients who are, retirement age, right? I know the age difference exactly. And so this data set was released by CMS in 2014, and it includes payment information from the year 2012 for about almost 1 million providers and 5,000 CPT codes and about 10 million records. It's a little bit aggregated. It's not individual claims, so it's aggregated, so they wanted to prevent having patient information, but it's still useful. And every record in this has a lot of different fields, and we'll use only 4 of them, so I'll show you which ones they are. This is an example of the actual, 5 records of the actual file, and this is what we take out of it. So we decided to take, the first field here is called the NPI. That's a provider ID. That's the doctor. This is an ID of the doctor. Every doctor in the US has an NPI, which identifies that. The second one is a specialty. In this case, we have internal medicine, pathology, etc. The third one here is a CPT code. This is a procedure code. This is what am I claiming money for? In this case, this person did a tissue exam by pathologist. And this is the code. And the count is how many times did I do this in the year 2012, right? So there's also the money that I didn't include the fields about, for example, the money that I asked for this, but we just took the count, okay? So these are the 4 fields I take out of this. And then our approach is, first is going to be this data preparation. Then we're going to compute similarities. Yes, question?
Wouldn't it be useful to also include the locations of the doctors and where they serve? Because if there's some kind of fraud going on and the doctor's in a practice or the doctor's in a hospital, then it's more likely that there are other doctors also in the same practice or also in the same hospital.
Yes, the question was, isn't it useful to get also information about the geographic location of the doctors as a feature in describing it? So not for this thing, because this is, again, creating a feature in your model, but absolutely in a completely, the rest of the supervised model, there will be absolutely a must-have feature, so I agree, right? So, does that make sense? Okay. So, you'll see how this is integrating into a larger model. I'll show that at the end. So, so we do data preparation. We compute similarities between doctors. This is important. The idea is, I want to find out if Dr. A is similar to Dr. B, and in a particular way that's important for the algorithm, and I'll talk about this. And if me and Demi are similar doctors, then we'll both have nodes in the graph, and we'll have an arrow or a line between us as a connection in the graph. So similar doctors will be connected to each other, and non-similar doctors will not be connected. That's why we compute the similarities and we build the graph. And then we compute PageRank with a variant that's called personalized PageRank or topic-based PageRank, and use that to create those features that help us identify anomalies. Okay. So now I'm going to go into each of these 3 steps, kind of a little more detail. Step 1 is actually relatively easy in this case because the database has been cleaned for us and aggregated. So in this case, this is the 3 lines that you saw earlier of 3 different things. So what we do is we just filter and create the columns that we want, right? It's just really a simple selection, nothing to this. So the problem is that we found that the specialty string there was actually not accurate in a lot of cases. It was all or something. I don't know exactly why, but we found after working this for a while that the specialty was not good. So we had to recompute the specialty from 2 other data stores. So I'm not going to go too much into this. You can again look at the code on GitHub because it's not really important for this particular case. I just wanted to mention this. And the other thing is there's a lot of different counts. It turns out that when you count, if you did an X-ray, you could count it in a lot of different ways. You can count how many you did in a year, how many you did in a year, normalized per day, if you did twice for the same patient. There's all kinds of weird things like that. So we selected a particular one called Benedict Services Count. If you're going to follow the code, you can look that up. That's one of those fields. They have multiple, and we chose that one. In terms of the cleanup, as I said, some of the specialty values were inaccurate, not specific enough. So we ended up looking at two other data sets, the NPI data set that's publicly available and the NUCC data set, and from that we mapped the NPI to a specialty code and the specialty code to a specialty string, and then that's how we did that. So I'm going through this a little bit quickly. This is what I wanted to get to. So how do we compute the similarity? So again, we wanted to make sure that two providers are similar if they have the same procedure code patterns. So if I'm a, let's say, X-ray specialist, then the procedure codes, the CPT codes, should be very similar to other X-ray specialists. If I'm a cardiologist, I'll have the same pattern of cardiology too. So the idea here is to represent a provider, a doctor, as a set of these 5,000 or so, 6,000 procedure codes. Think of it as a vector, and you put the count in each cell based on the procedure codes that they've done. And we expect that these two providers that they have are similar specialty will actually look the same. They'll have reasonably similar, they'll have zeros in all the stuff they don't do and some numbers in the stuff they do and reasonably similar numbers, right? Or close. And that's how we do it. So we use cosine similarity. Again, there's a lot of other similarity functions we could have used, but we chose to use that. And each provider is represented as this vector, and we just compute a similarity function, right? Here's a very small example. Of course, this is just 5 codes, not 5,000, but again, you can see these are the CPT codes, these are different procedures that I just chose randomly, and you can see that these two NPIs these two doctors look very similar because they're only different in one thing here, and the numbers are pretty similar volumes, etc. So that's how we do the similarity. Now the problem is that computing the similarity is actually a pretty big problem. Because we have, let's call it, we have 880,000 providers, let's call it 1 million, right? That's 1 trillion computations, or if you want the exact number, 77 something billion computations, which is a lot. And each one of those is a dot product with just, a big vector. So there was something that we wanted to parallelize and make it a little bit faster than just running a single machine. That's what we use Hadoop for in this case. So what we did is we created a few heuristics to help us kind of filter, phase one. One of them was that we only compute the similarity between two NPIs if they share the most important CPT code. So if you're a cardiologist and you do a lot of heart surgery, then you'll have a bunch of different heart surgery things that are most important for you, and we'll compute the similarity between you and another. Oops. Oh, okay. Yes, no? Sorry, maybe I should move. So you compute this, if you share the main CPT because it's the most important for you, which we define as a certain percentage of your CPT volume. Okay, thank you. And then we also, some doctors have just very few claims in this data set. So if you had less than 3 CPT codes, we said, we're going to throw you out. It's a easy, lazy solution, but we just wanted to do that just to show the case. Because if you have less than 3 CPT codes, maybe the cosine similarity is just noisy because it doesn't have enough data to show anything. And we used Apache Pig. As you who know, Pig is a kind of a scripting language on top of Hadoop with some UDFs in Python to compute this in parallel. I wanted to mention before I go into this one step further, there are alternatives to compute similarity at scale. One of them is called DIMSUM. It's implementation of, it was a MapReduce implementation initially implemented at Twitter by a Stanford professor. And it's a probabilistic implementation that also solves this big scale problem, makes it faster. There's another one called locality sensitive hashing, or LSH, which allows you to do, for those of you who don't know, LSH is a way to quickly compute k-nearest neighbors in really large data sets. So those are 2 other options we didn't pursue at this time. We could have done that too, and maybe it's better, maybe not. This is the code in Pig. I intentionally made it small because I don't want you to read this. If you want to read it, you can go to GitHub and read it in more detail. It's also kind of a part of it. But I wanted to highlight that it did end up being a good solution. It saved us a lot of time in running this. Even after this in Pig, it's still running it on a single machine. Even in Pig, it takes about maybe 2 hours to run end to end, so it's not simple. And what we use here is a couple of Pig tricks, like using replicated joins, what's called website joins. We had a big problem of data skew. Some of these doctors are very similar to a lot, or we suspected would be very similar to a lot of other doctors. And some communities of similar doctors had different sizes, and so some of the computation happened on a node that had to compute a lot, and some other had to compute a small node, and we had to wait for the big node's computation to end, and so ended up doing a couple tricks to distribute the computation a lot more smartly. So we did that, and we used some Python UDFs to compute similarity, break like large big bags into smaller bags. We could have used other Java as the more natural choice, but Python is easier to show in code and explain. So it's a little slower, but it's just easier to work with, and I like Python. So that's the reason, no other reason. Okay, so now we have the graph. Remember, we have nodes or doctors, and we have a connection between two doctors if the doctors are similar to each other. Now starts the really interesting part. So there's this thing called personalized PageRank. And what we're going to do is, we're going to do a specialty-centric, I'll explain what that is in a minute, personalized PageRank for each node, and, which is a provider. So you take the graph that has just links and nothing to it. At the end of this process, you get to a certain score of each node. So if you choose a specialty, let's say cardiology, pick on that one again, and you say from a cardiology perspective, the score represents how likely this person is actually to be a cardiologist, okay? And if you have a really high score, but you're not a cardiologist, that's kind of strange. That's the main idea of why this is kind of anomaly detection, okay? So let me first explain what PageRank is. PageRank is the algorithm that was used originally by Google. That's one of the main reasons that they became very good in search when they started. Sorry?
Larry Page, but not a...
Yeah, people say it's Larry Page after him, it's Page on the web, there's a lot of reasons. But PageRank, essentially what it does is there's a lot of different interpretations to it, how to explain it. I chose one that's called the random walker interpretation. And so think of a graph, and usually it's a web graph, but I did the doctor graph here. So we got these nodes in the graph, and there's a person that's a random walker. What that person does is start step 0 and walk onto a random node in the graph, okay? And then each iteration, what you do is you either, with a certain probability, you either walk to an adjacent node in the graph, okay? And equally, so if you're in a node that has 3 adjacent nodes, then you can move to you'll move to either of them with 33% probability, so equal likelihood to do that. Or you might teleport into a random node in the graph. You just kind of hover and choose another one and randomly blend there.
Is that kind of a sampling or what?
Sampling? No, it's not a sampling. That's how the algorithm works. So usually people use something like 80% probability to move to an adjacent node and 20% to move to that one. And the nice thing about this algorithm is that and this is kind of, by the way, this is the formula that you look at it, the PageRank is defined like this. And when it converges, and there's a proof to show when it converges, then in the web, what it did is it represented the likelihood that the random walker will end up in each one of the nodes. Okay, so you can imagine if it's a very tight set of nodes, nodes that connect to a lot of other nodes, it's more likely you'll end up there, and if you're very distant, you might not, and things like that. But that's what PageRank is in general. By the way, they told me to say all doctor names here are fictitious. None of these guys are, anomalous or fraudsters or anything like that. It's just completely random choices. So in the personalized PageRank version, what happens is we do a similar thing. However, we focus on a given specialty. So I color-coded the nodes here. So imagine that the red are the specialty group, certain specialty group. The blue is another specialty group, and the yellow is another specialty group. So maybe cardiologist, dermatologist, and internal medicine, for example, right? So at each step, here the walker can move to an adjacent node, or randomly jump to any node in the graph, but in this case, only the nodes in the specialty group that was chosen. So if you focus on cardiology, which is the red, the teleportation happens only to the specialty. So that creates a special focus on those nodes, and as you can imagine, when you look at the properties of this algorithm, they get higher probabilities. So it's more likely that you end up there because you can only jump randomly there versus all the other nodes. If you choose another specialty group like the green, you'll get those guys to be a little bigger and the other guys to be a little smaller. So that's our simplified version of personalized PageRank here. And we use this on our graph, and this is the code to show how you do it in SociaLite. And this is another interesting part of SociaLite. A lot of graph algorithm packages, Giraffe is one of the famous ones. You have to write code, Java or Scala or whatever it is, to implement your algorithm. The thing about SociaLite is that you actually write kind of the equation of what happens. So I'll walk you through this code a little bit to show you what I mean by that. So here, everything that's in the backtick is like SociaLite code, and the rest is Python, so it's kind of very integrated in Python. So what happens here is you say, I'm defining a table called rank that has these 3 fields, NPI, iteration, and rank, which is the page rank that we're computing. I'm initializing it to 1 over n. N is the number of nodes in the specialty that we defined earlier. So the initial page rank is 0 for everything else and 1 over n for all these specialty nodes. And then we do 10 iterations here, which we found was enough. And literally, if you look at this is sort of similar to actually the equation of PageRank. You say the PageRank iteration I plus 1 will be 20% if you go to a random node in a specialty, and this means this is the 80% if you go to an adjacent node. So I can go into a little more detail, but I don't think it's very important. And this is all the code for this algorithm, and then SociaLite takes this and translates it into actual code that runs and computes this very efficiently. Because it's kind of it's almost like a SQL for graph algorithms. So because it's very high level, it's actually pretty efficient. So that's the code here, and then so what I like about SociaLite, yes.
By the way, where is that executed? Like when it's translated, is it distributed or single machine?
So SociaLite at the moment doesn't work on Hadoop. It reads data out of Hadoop. I've asked G1 that I thought it was a good thing for him to support that. He didn't do it yet. It was just one student doing a PhD, so I can excuse him for that. But it does have a distributed version that runs on, if you have multiple machines, all writing Python, you have to run some server there. You can actually run multiple SociaLite instances and run it in parallel like that. We actually, in our demo, ran it on a single machine, and it was very fast that way. We didn't need, even though it had, I think, 500 million edges and about almost 1 million nodes, it ran, like 10 minutes. It's not a big deal. Yeah, it was very fast. But you can run it on multiple machines, so it supports that. So what I like about it is, you saw it's PageRank is like 3 lines of code. I mean, you gotta understand the little kind of definitions of it, but it's really nice. It has Python integration, so you can do a loop. If you've seen here, I've done a loop. This loop is in Python, and some of the variables like I comes into the, so it's very integrated in Python. It's kind of really nice that way. And you don't have to think like a node. It's a declarative language, and it kind of looks like the formula, which is pretty nice. So that's SociaLite. So the end of this is when you run it for a certain specialty, let's say cardiology, and you get these scores of all the graph. And those scores themselves, that number is a good feature to use in the system. So if you have a system that, to answer the earlier question, if you have a system that has claim information, patient information, provider information, it creates features for a supervised learning model to predict if it's fraudulent or not, puts this into a fraud model, maybe add some rules on top of that to make a decision whether this is fraud or not. What we're suggesting here is that you run this PageRank scores that generate offline, and there are a provider feature, if you will. They represent a provider. So out of this provider of this claim, you can pull the provider score for each specialty and add them as features here, and then you get a better result out of this. Now, the next question will be like, how do you know that this is working? Well, I would like to know better than I know, because I don't have this system in place to use it. So we did a proxy for that. We kind of tried to prove to ourselves that it works. And the way we did this is we kind of looked at examples and eyeballed them. Ideally, I would like to have a system like this where I can actually put those features in and see that actually my model with the features instead of without the features works better. What we did is we just looked at examples, and I can show you some examples that I think will prove to you this is actually a useful feature. Here's two examples. This one is ophthalmology, which I think is eye doctor. Okay, so when we ran it on ophthalmology, we found people who are internal medicine who have these CPT codes, these procedure codes. They do a really long list of eye stuff. So that was kind of suspect. And again, I don't have doctor names here. But the other one was a little smaller one, but I have plastic surgery as, somebody who's a otolaryngologist. Why did I choose these bad examples? But ENT, ear, nose, and throat. Okay, so we found somebody who looks like a plastic surgeon. Now, does it mean that they're fraudulent? Not necessarily. I mean, people change specialty. Maybe they've done something off for somebody else. We don't know all the details, but it's very likely that if they look like this, maybe they are, and you want to know about this. This is what the importance of a feature is. So those are the two examples I have. And I'll take any questions about this, about Hortonworks, about Hadoop, whatever you want to ask. Yes?
Could you elaborate on about what was the intuition of using PageRank for this kind of data? Because PageRank for web pages, the intuition is very clear, links on web pages. Now, these connections between doctors that you define as similarities are less obvious.
So the question was, what's the intuition between using PageRank for this application as opposed to web pages, where it's much more, I would add to what you said, much more established, much more proven, has been used for many, many years. So, as I said, our starting point wasn't intuition. Our starting point was, I want to show something with graph algorithms, and we looked at different ones, and we eventually ended up looking at this. It looked like a good idea. The intuition, but there is strong intuition. The intuition here is that if you start with a personalized PageRank, so you start with a focus on a particular set of doctors, people who do the same, have the same specialty. If you're an X-ray person, right, or if you're a cardiologist, you should be similar to other doctors in your profession. You should be doing the same procedures, the same type of treatments to your patients. And if you're not, maybe you're more generalist and you do a lot of different things. And maybe you're doing some procedure that's not what you're supposed to do. So that was the thing we wanted to capture. The similarity is in itself as one number is not very perfect, but when you put it in a graph context, that means that if you start with a random walker, think of it this way: you start from one of the specialties. If you end up getting to somebody who looks very similar to a lot of different people on average, in sort of in a probabilistic manner, if the random walker ends up with somebody who has a lot of probability in that graph, in those PageRank scores, then it probably looks similar to a lot of other people who are cardiologists too that we started from, but they don't have the specialties. That was the intuition behind it. There's a couple of different things that are different here than the traditional PageRank. One is that usually the graph is actually one-sided, so there's arrows, like there's hyperlinks between this page and that. Here we use the bidirectional connectivity because we figured that symmetry actually here makes sense, because if I'm similar to you, you're similar to me, right?
So it's one-directed?
It's one direct, yeah. Does that make sense?
But that means that it doesn't make a difference if we use lead propagation as well, for example, any other algorithm that doesn't score propagation. Is it correct?
So belief propagation is a whole, I think of it as a little bit of a different type of algorithm. Are you asking if belief propagation might work here, or it might? We haven't tried it.
According to what you say, it's also appropriate.
It may be. My concern would be that, so belief propagation is part of, Bayesian networks maybe, or things like that, and it's just much less scalable algorithm. Belief propagation tends to be computation. My limited knowledge is it's much more difficult to compute at large scale, but it's something you can try, definitely. Yes?
So I'm wondering what your false positive rate is, because given that your model is attempting to pull out any sort of non-uncommon behavior, so there's a couple of instances I can think of where that sort of thing would be more acceptable. One is where a doctor is prescribing some kind of experimental treatment, which necessarily is not something that's necessarily accepted by the wider medical community, but is something that the doctor may, it can be very legitimate. And the second one is, of course, the natural disagreements that doctors have in their field. Some doctors who will simply prescribe the most expensive medications for their clients because they, the newest and greatest medications, and other doctors may say, well, there's this older medication that might have a slightly lower percentage of working, but it's been in use for 20 years, and there's a generic version, so it's much cheaper for the patient. And so they would disagree with their both legitimate. So how many cases like that come out?
So the question was, have we seen a lot of false positive rates, and how many cases like that? So first I would say that, again, as I mentioned earlier, unfortunately we don't have a system that knows the current model of testing, and we can add it as features. So we had to really use our kind of common sense and eyeballing of this. But I would tell you that we found, initially, the reason I mentioned earlier that we had found that a lot of specialties were wrong. This is actually how we found them. Initially, we didn't know that, and we found a lot of false positives that ended up that we saw a cardiologist that looked like something else, and we're like, that's a good example. We're very happy with ourselves. And then we kind of Googled around with the NPI, and we saw that the doctor was actually, in another place, was quoted as having a different specialty, was actually appropriate. So that's how we found that some of the specialty codes were not correct, and we had to do all this work to clean it up. Other than that, I don't know what the false positive rate is. But remember that it's not a system on its own. It's just a feature that goes into another system. So the way I would evaluate it as a healthcare organization is I would take the system you have for fraud detection, I would put those features in, and I would evaluate does it find new things? And usually the way this works, it's not like you go and you kind of send an email to the police people to arrest this person. It goes through, it's a trigger. You go and you get it evaluated, you get some investigation team that go and check it out, and they can apply some of these things. But if the false positive, I agree, if the false positive is going to be way too large, then it's not good.
But naturally, the fewer false positives, then the less that those companies have to make those phone calls.
Absolutely.
The less of those people that they have to employ.
Absolutely. So you're right. We wanted to have false positives, but I don't have the number. I think it's a little bit less of a problem because there's a lot of other features in there that the algorithm, the overall algorithm, decides on. But yes. Other questions?
And about the
Yes.
feature selection, how long did it take to actually filter the data to understand which of the features are really relevant or more significant, and about the computation side after?
In the Medicare-B data set?
Yeah.
So it's a pretty simple data set. I mean, it's got maybe 29 or something fields. So we had to read, they have good documentation on it actually, funny enough. The only complication was to figure out, should we use one of the ideas was that we should use the amounts instead of the counts of how many, because we use the counts to say, this doctor is similar to the other doctor if they have the same amount of CPT codes. And we said, why don't we use the dollar amounts? That turned out to be a bad idea, even though initially we were like, this is probably better. Because dollar amounts, there's a lot of contracts between providers, and there's a whole world of contracts, and the amount you get paid may be different for different providers because you have a different contract with the insurance company, and so you won't find that people are similar to each other because of that. So it turns out that the counts are actually a much better indicator of similarity for this purpose.
Maybe even the frequency of the procedures.
Yeah, and again, this was a demo. This is not a running, we didn't run it on a real healthcare. We wanted to show the way to a lot of healthcare companies and try to prompt them to try to use this. But you're right, there's every decision in this algorithm, I want to say this up front, is not necessarily the optimal one. Okay, there could be, you could use, instead of constant similarity, you can use something else, you can clean the data better, you can, instead of counts, you can use log counts or some other normalization. There's a lot of different decisions, and when you do this in a real world application, you want to explore all of these and optimize for what's the right way to do it. Yes, there was another question there? No? Okay. Yes?
So you ran on some real data set. Didn't you find any data that is worth reporting?
As being a company, we try to get away from that. We don't want to go into the legal aspects of it, and I'll keep to that perspective for now. Yes?
Have you considered crossing, for example, PageRank with Medicare, basically a sentencing database with medical payment database?
Say it again? Yes.
There's a database called PageRank. It contains all the legal proceedings in the United States. Federal courts in the United States.
Okay.
So you can find the sentencing in the medical cases and use it as a learning.
So the question was, there's a database I didn't know about. This is called the BASEP. Okay, something like that. That has all the legal proceeding outcomes, and you can filter that by medical proceedings, and then and look at those and say, and say those will be good things to look at where somebody was actually convicted of fraud, and then match it with that. No, we haven't tried it. It's a nice idea. My concern would be that maybe there's not enough of those that map to the year 2012. I mean, this is a very specific data set.
I think we're close to the speakers or something like that.
So maybe there's not enough cases there, but it's an interesting idea. We haven't tried it. Anything else? Yes?
How would your algorithm deal with the doctor that just does something strange and it is not similar to any other specialty?
So the question was, how will the algorithm deal with a doctor that does something different but is not similar to any other doctor, or not to very many doctors maybe, right? So I think if you have a doctor that just has a pattern of cases that's just pretty random and not similar to anybody, they would probably be isolated in the graph, in which case they would not be recognized. So I think maybe that's a weakness of the algorithm if you kind of do a lot of different things like that. But think of it in reality, I mean, you just have to have all kinds of equipment and all kinds of things in your clinic, right? It's not realistic that somebody will sell you, you don't control the procedures you do, you can only do the stuff you have equipment for in your lab. So, but I think mathematically it'll probably not be matching anything. It won't be similar to any other doctor. It'll just be maybe matching one or two doctors, and it'll be there on the side and get a very low probability for all specialties. Internal medicine people actually look a little bit like this. There's another thing I didn't mention, nurses, for example. We removed them from the algorithm. If you look at the code on GitHub, you'll see. Because there's a couple of types of nurses codes that we removed, because nurses help all kinds of doctors. And they would actually look like this. They have all kinds of things, because sometimes they help this department, the next day they're in this department, and so they build their own codes, and therefore they look very random. So yeah. All right. Thank you very much.
Thank you, Ofer, for the interesting session. I enjoyed. I hope all of you enjoyed as well. Like all of our meetups, we film these meetups as well. You can see this meetup video in about a few days in our YouTube channel. And the slide, some of you picture the slide. There is no need to do it because we will share the slides in all of our groups in all of the social media that familiar to you, Facebook, Twitter, etc. Thank you.